So engineering notation in standard form, something that you're going to be using a lot if you've not done already in your units that you're doing. You might well have seen numbers expressed in this way, because it's a way of representing very big or very small numbers. There's a number, a very big number. The decimal point is here. And if I want to express this number in standard form, I shift it to after the first significant figure. So it equals 3.6. So that means I've moved the decimal point to after the first significant figure. But then I'm going to have to multiply it by 10. How many times to get it back to where it should be? To get it back to where it should be. So there it is now. I've got to go there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So multiplying 10 times. And that's in standard form. The decimal point is always after the first significant figure. So you might want to make that note if you've not seen these things before. That's how I would express that very large number in standard form. In engineering notation, the power has got to be a multiple of 3. So let's just focus on this, what we can do to do that here. Back at the problem. Here's the decimal point, that's where it should be. Bear that in mind always. So then I say to myself, okay, this at the moment is telling me I've got to shift the decimal point 10 places to the right to get it where it should be. So if I were to actually shift it one place to the right to make it 36 point something, then now how many places have I got to move it to get it back to where it should be? Right. So times 10 to the 9. Now it's in engineering notation. The power must be a multiple of 3. The power must be a multiple of 3. So, or I might decide I don't want to do that. Actually, I want to shift it so that the decimal point is here and call it 36,000. Now how many times have I got to move the decimal point to get it back to where it should be? Right. So that too is in engineering notation. Equally valid. Because the power is a multiple of 3. And then we're down to deciding what units we want to be in. So that brings us to the idea of prefixes. So we use multiples of 3 to fit in with prefixes. Oops. Prefixes. And the common prefixes for large numbers are kilo, 1,000 or 10 to the 3, mega, 10 to the 6, and giga, 10 to the 9. In fact, nowadays with computers we're going to the next level, which is tera. So let's put that in now. 10 to the Well, goes in threes. Okay. So as an example, we might have a kilo joule for energy. We might have a megajoule for energy, or a gigajoule for energy, or a terajoule for energy. And if you end up working at CERN or somewhere like that where these machines generate massive amounts of energy, then you're talking about terajoules of energy. So which of these do we use? 36,000 times 10 to the 6 or 36 times 10 to the 9. It all depends on the units that you're routinely using. If you're routinely using the megajoule, if you're talking about energy, then you'd call it 36,000 megajoules, and so on. So there's no right answer to that. All depends on the scenario. So that's engineering notation and standard form for large numbers. What about small numbers? Same situation, or same idea. I'm going to move the decimal point from where it is to somewhere convenient. Right, in engineering notation it might well be there, yes, because it will then be a multiple of 3. In standard form though, it has to go there, between the two numbers. In other words, after the first significant figure. So in standard form, this would equal 3.6 times 10. Now this time, when we come to the laws of indices, we'll understand more clearly mathematically why this is the case. But if I've shifted the decimal point to here, I now actually don't want to multiply by 10, I want to divide by 10. 1, 2, 3, oh, I've lost count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ooh, 10 to the minus 10. So divide is minus power, because minus means the inverse, as we'll see. So instead of multiplying by 10, we're dividing by 10. And we indicate that with a negative sign there. So that means a small number. That means I'm going to the left 10 times to get it to where it should be. Okay, Gavin? And that's in standard form because it's not a multiple of 3. So as you quite rightly indicated, if I wanted it in engineering notation, I'd write 0.36. So if I shifted it one place to the left, how many more have I got to go? Right, so times 10 to the minus 9 would be in engineering notation. Yeah. We will be sticking to engineering notation. So I mentioned standard form because you'll come across it, you see it in the text, but we'll be using engineering notation. Yeah. And again, the reason why we're going through it is because of the prefixes. So what are the prefixes involved here? We've got milli, which is 10 to the minus 3. For example, millijoule. Note little m rather than big M for mega. Next, micro, 10 to the minus 6. And we can't use little m because that's milli, so we use this symbol here. And this symbol looks like a U with a tail on it, like this. Whoops. Like that is the Greek letter mu, M-H-U, and that's used to represent micro, always. So that's a common symbol to represent micro something. The Greek letter mu. 10 to the minus 9. No, that's the next one. Yeah. Nano. So nanojoules. these sorts of prefixes become useful in electrical work when we talk about farads and capacitors. We normally talk about microfarads or nanofarads, or even 10 to the minus 12, which is pico. So little p. Oops, we've got farads then. Joules. So we use small case letters for these. And so this one here, the one that we've been looking at, 0.36 times 10 to the minus 9, could be written as 0.36 nanojoules, or if that's what we're talking about, joules. Okay. Okay. Last little exercise then before the break. We're going to use these numbers that I introduced you to, okay? The charge on an electron and the number of electrons in 1 mole of material. A small number, a big number. First job, what's that in engineering notation? And you've got a choice here, you can either go left or right. So what are you going to say? So what are you going to write for engineering notation? Right. Okay. One place to the left, so only 19 to go. I could have gone the other way and called it 160 times 10 to the minus 21. What about this one? That's not in engineering notation either, so what could I do with that? At the moment, I've got to go 23 places to the right. No, I can see why though. No, I've got to go 23 places that way. So if I shift it once, how many more have I got to go? 22. Twice? 21. So in other words, it's 662 times 10 to the 21. I'm going the other way with big numbers. So that's these numbers in engineering notation. So now you can enter them into the calculator, either like that or like that. It's the same number. Find out what Na times the electron charge is. Can we estimate it before we put it in? Thinking about what I was saying earlier. When we multiply numbers, we add the powers. So estimate this. Round that to one significant figure. 2 times, round that to one significant figure, equals 14 times 10 to the, what do you do with the powers? 10 to the 4, roughly, yeah, 23 minus 19, 4. So I'm going to expect something roughly 14 times 10 to the 4. Now do it on your calculator. So 105 times 10 to the 3 in engineering notation. Yeah. And that will be in coulombs because it's a charge. So 105 times 10 to the 3 or 105,000. When you get small like this, you might well just write the whole number. That's 105,000 coulombs. So if you look up the Faraday number, you should find that it comes to around about that. If you want to look it up, I'll leave that up to you.